Hello, this is section 3.8, which is about hyperbolic functions, which is a special kind of function that you probably haven't seen before, and it's not a very long section. This should be pretty quick, but we're going to start with a couple functions, just given their basic formula here, differentiate them. Let me give you a big hint before you do that, which is that you can write this as the divided by 2 is the same thing as 1/2 times e to the t minus e to the negative t. That will make it so you don't actually have to use the quotient rule with these. So give these a shot. Let's differentiate them just to get a little practice, and then we will see what these hyperbolic functions are. So let's pause it, and the answers will appear in 3, 2, 1. So here are the results. So yeah, the 1/2, the fact that it's divided by 2, when you factor it out, you see it's a constant multiple of the whole function. And with constant multiples, you can just take them out, leave them alone, and do the derivative of everything else, and then just multiply it by 1/2 after. So that's what we did here. So the derivative of e to the t is just e to the t. Then the derivative of e to the negative t here, this requires the chain rule, because negative t is its own function that isn't just t. And when you do the derivative of it, you end up with a -1 here. That you have to multiply it by. So then that negative, and then times another -1, those basically cancel out, and you end up with a positive here. And that's the answer to this. And notice that f prime of t, the derivative of this first one, is actually exactly the same as g prime of t. I'm sorry, just the original g of t with the plus here. And then g prime of t works out basically the same way, but it started with the plus in between them. And then when it gets multiplied by the chain rule derivative of negative t here, which is -1, that becomes negative. So then g prime of t is actually equal to the original f of t, which is kind of a weird thing. So these two functions are derivatives of each other, which is a little weird, but it is true. And these are actually, I didn't tell you, but these are the hyperbolic sine and cosine functions. And let's look at a definition of them here. Let me cover this bit up for a minute. So yeah, so the g of t one there is cosine of t with the plus hyperbolic cosine of t with a plus in front of them, and with the minus, this is the definition of hyperbolic sine of t. And usually we just pronounce these as best we can. Like, I don't want to say it cosine, and if you use these a lot, you don't want to say hyperbolic cosine over and over again. So people usually just say cosh. I don't know how else to spell it. Maybe with an A or something. Kosh. But that's how you say that. And then there's no good way to pronounce an N with an H after it in English, so we just call it cinch to make it so you can pronounce the H somehow. If you want to call it cinch of t is the nickname for this function. And at this point, you're probably wondering, what the heck do these have to do with cosine and sine, and what do they have to do with hyperbolas? Why are we giving them these names that sound like it's a weird name for a function, that like it's more like an exponential sort of function than a cosine, right? So just to help understand that, this next thing here, you maybe don't need to write it down, but I think it's interesting, so I'm going to tell you about it. But yeah, you don't necessarily have to have this whole thing in your notes, but you'll probably find it interesting too, so I'll tell you about it. So if you take a unit circle over here, radius 1, the equation of the unit circle is x squared plus y squared equals 1. And if we're using radians, let's think about the relationship between this angle and the area inside of the sector. So remember with radian angles that the angle equals the arc length. That the arc length that angle subtends in the unit circle. And you know, the total circumference all the way around is 2 pi. But we also know that the total area is pi. So what I want to do is figure out what is the area of the yellow part in there of the sector in terms of theta. So the total circumference, the total distance around is 2 pi, but then the total area inside is just pi. So if theta was 2 pi, then that would be like the sector was the whole circle. Then the area inside that sector would just be pi. So another way of looking at this is saying that the fraction of the total circumference is theta over 2 pi. So for example, if theta was pi over here, that would be half of the total circumference. That would be pi divided by 2 pi would come out to 1/2, which makes sense. Or if theta was 2 pi, this would be 1 or 100%. Right now, I would say that this theta looks like approximately pi over 3. It looks like 1/6 of the whole thing. So we could say that this is about like 1/6 of the total area. And if you do, anyways, that fraction times pi, so to get that fraction of the total area will get you this theta over 2, because that cancels out. So in other words, the area of the sector here is theta over 2. So that's interesting. So that actually turns out you can give this alternate definition of cosine and sine. You could say that cosine of theta is the x-coordinate here. The x-coordinate is cosine of theta on the unit circle, corresponding with a sector with area theta over 2. So it's kind of like saying another way of defining what cosine is it's not just this x-coordinate, and sine isn't just the y-coordinate here, but you could pretend we're plugging in double the arc length, double the area of the sector, and then getting the corresponding x and y coordinates that relate to that. And it turns out that hyperbolic sine and cosine actually do basically the same thing here. So if you take a basic hyperbola, which is sort of like the unit circle, it's just instead of it being x squared plus y squared equals 1, it's x squared minus y squared equals 1. So this is like a basic hyperbola. And if you take like a sort of hyperbolic sector sort of thing here, which looks like the same idea as with the unit circle, and you say that this area is t over 2, like that number t essentially defines some xy point here. If we take that number t and then divide it by 2, so t is really double the area of the sector, and then plug it into this thing, it turns out, I'm not proving this, so you'll have to believe me, but it turns out that cosh of t is actually this x coordinate right here, and sinh of t is the y coordinate of that point. So they have that. So hyperbolic sine and cosine have that same sort of relationship about the area of that sector as regular old circular cosine and sine have with a circle and the area of sectors in a circle. So that's where the name comes from anyways. You don't really need to know this fact, but if you're wondering why on earth would you call this weird exponential function cosh of t, or hyperbolic cosine of t and hyperbolic sine of t, where does that weird name come from? That's why. But So, but you don't really need to use this. You don't need to know anything about hyperbolic geometry or anything. We're just going to use the formulas. And yeah, you just proved something about the formulas, what we did up here. You just showed that the derivative with respect to t of cosh of t is equal to sinh of t, and the derivative with respect to t of sinh of t is actually equal to cosh of t, which we just figured out here. So that's a thing you should know. You should know that fact about the derivatives, and you should definitely know these definitions of them. And that's the only thing from this section that you really need to know. So for the rest of this, we're kind of just going to practice that. But let's actually, if we're not really proving this fact over here, we might be able to at least verify that cosh of t and sinh of t are actually a point here. That is, if you plug in cosh of t equals x and sinh of t equals y into that equation, then it will work out. So let's do that one here. I'm going to just replace the x coordinate here with cosh of t and the y coordinate with sinh of t, and use the definitions for those functions. Here's that step with just replacing the x with cosh of t and the y with sinh of t. Now I'm going to replace each of these things with the definition in terms of the exponential functions here, which looks like this. Next, let's just take each of these fractions and square the top of the fraction, also square the bottom of the fraction, and see how that works out. So 2 squared is just 4, and both of these denominators, and squaring the top with these binomials in each means we have to FOIL that out. So let's FOIL that out here. We get this result. Let's see how this all came out. So first, if you do e to the t times e to the t, let's just remember that, like, if you multiply e to a power times e to a power, that's the same as adding the exponents, just a reminder of that rule there. So doing t plus t gives you this term here. And then if we do, let's say the outer terms, e to the t times e to the negative t here, that will give you an exponent of t plus negative t, because we're still adding those exponents, and that gives you this e to the power 0. And likewise, the inner terms here, e to the negative t times e to the t, gives you e to the 0 as well. And then the last terms here is the e to the negative t times e to the negative t. That results in e to the negative 2t. So that's how that worked. And in the other one, everything would be the same. The only difference is that a negative e to a power times a e to a power should end up being negative. So both of these are negative and everything else is the same. Now we're going to have to deal with this minus here and subtract all of the terms in this one. We can combine them because they have the same denominator. So once you've subtracted all of these terms like this, so all of the signs change when we subtract the whole fraction, and it's still all over 4. There's a bit of canceling stuff out we can do. We have e to the power 2t here, and that's minus e to the power 2t here. So those cancel out. E to the negative 2t minus e to the negative 2t, that cancels out. And you see what we're left with is just 4 over 4 equals 1. And that is true for all values of t here, because all of the t's cancel out. It doesn't matter what t is. So this is an identity for hyperbolic sine and cosine, that because it is a point on this hyperbola, x squared minus y squared equals 1, we can write this as cosh squared of t minus sinh squared of t equals 1. This is like the hyperbolic equivalent of cosine squared plus sine squared equals 1, which is what you have with a circle. Okay, so I do want to point out here that these functions actually do have applications in the world. We're not just studying them because of this weird property they have with hyperbolas. It turns out, and I don't want to spend too much time trying to prove this, but this here is just the Wikipedia page for catenaries. So the name of this shape is actually called a catenary, and it turns out that when you have hanging cables, they always form the shape of a Cauchy curve. And you're probably thinking, wait, that looks like a parabola there, doesn't it? It does look like a parabola when you have hanging cables like these. Oh, here's a pretty one. Those are actually a lot of hyperbolic cosine sorts of equations. And if you're thinking that these, like hanging cables like this, form a parabola, it actually doesn't. If we look at the shape here of two of these, the green graph here on the bottom is a graph of the basic Cauchy function, and this black one right above it is a graph of a basic parabola that has like the same vertex as this, and they look pretty similar. It looks like Cauchy is like a parabola, but zooming out a bit, we can see they end up having kind of different shapes. So a parabola starts out kind of increasing a little bit more fast, a little bit steeper here, but then pretty soon the Cauchy curve gets bigger. And if we zoom out a little bit more, you can see that like they're really not quite the same kind of shape. So it turns out that hanging cables do not quite make parabolas. They actually make catenary curves, which is the name of a hyperbolic cosine thing. So it is a thing that comes up in engineering. Now, there's other kinds of examples of this. It turns out it makes a pretty strong archway if you turn a hyperbolic cosine curve upside down. The St. Louis arch in St. Louis, I guess it's actually called the Gateway Arch, but I always called this the St. Louis Arch. That's a catenary curve as well. So that's what catenaries are used for, what hyperbolic cosine is mostly used for. Let's do one more example, this time with the tanh function. And the definition of the tanh function is what you might expect. It's the hyperbolic sine function divided by hyperbolic cosine function, and it comes out to be this thing here. So let's find the derivative of this tanh function using what we know so far. You can try this on your own or do it with me as I go through it here. It's up to you. But let's look at it. So I'm going to use this formula instead of using the exponential function formula because I already know the derivative of sinh and cosh. So the derivative with respect to x of tanh of x is the same thing as the derivative with respect to x of sinh of x divided by cosh of x. And to do that, we're going to need to use the quotient rule. And the quotient rule gives this result. It's a little tricky to follow, but that's why I tried to make the denominator here purple. So we've got low d high minus high d low over the square of what's below. And to get the derivative of sinh x, remember, is just exactly equal to cosh of x. So when you do the derivative of the top part here, that just becomes cosh of x here. And likewise, the derivative with respect to x of cosh of x, that's here, that's the derivative of the bottom, is just equal to sinh of x. And then the denominator, you just square that. So then you could write this as cosh squared of x because they're both cosh, and here you can write this as sinh squared because they're both sinh, and maybe you can see where this is going. Because when you do cosh squared of x minus sinh squared, that was this identity we basically just proved right here, which is that always results in 1. So you could write this as just 1 over cosh squared of x. So that gives you this nice formula, actually, that the derivative of tanh is equal to 1 over cosh squared of x. And you notice that's actually exactly the same as it is with regular old, the circular tangent function. The derivative with respect to x of regular old tangent of x is equal to 1 over regular old cosine squared of x. So they have that in common. So there's a lot of similarities between these hyperbolic functions and the regular old circular functions. So let's look at some practice problems. Let's try these using the differentiation formulas you saw above. So you might need to look at those. And for problem 2, we want to show that sinh is an odd function, just like actual regular sine is an odd function. So that means show that this is true. Plug in negative x into the regular sinh function and show that it gets you the same thing as this. So a little algebra practice there. So the answers for these, do these as usual. The answers will appear in 3, 2, 1. So with the cosh squared of x, this is just a quick application of the chain rule. So hopefully you got this if you're good with the chain rule. So the outer function here is written as something to the power 2. So the derivative of something to the power 2 is just 2 times that thing to the power 1 with the original inner function plugged in, which is cosh of t. And then we're multiplying that by the derivative of that inner function, which is sinh of t. So that just becomes 2 times cosh of t times sinh of t. And that sounds good. Then with practice problem 2 here, we wanted to show that sinh of negative x is equal to negative sinh of positive x. So I just took the formula for sinh and put in the input negative x everywhere. So that gives you e to the negative x. And then here we have negative negative x. That just cancels out to give you positive x. And then what I did over here is I just swapped these places. I wrote the negative one first, and then I wrote the positive one second. So the positive e to the negative x just got moved over here. And the negative e to the positive x got moved here. And I just did that because it works out easier to see that the result becomes sinh of x later on. But next I just factored out the negative 1 from the top to change the sign of this. So you have a negative positive e to the x here, and a negative e to the negative x. These negatives cancel out to give you that positive, so those are the same thing. And this is just the formula here for that whole thing here is the same thing as just sinh of x. So it is an odd function, and you can actually see that with the graph, if you know what the graph of an odd function looks like here. This is a graph of this orange or red one here is a graph of y equals sinh of x, and it has that kind of symmetry where if you plug in a value of x over here, let's say something like 3, then you get this y coordinate result up here is, oh, that's not straight. More like that. This is sinh of x. And if you plug in negative x, which is approximately negative 3 here, that's going to give you something like this. And then look at the y coordinate you get out from that. It looks like yeah, you get something like about negative 12. Like it came out to something around 12 with x, but if you plug in negative x, this y coordinate here becomes sinh of negative x, and it looks like that's equal to the opposite of sinh of x here. So this y coordinate is the opposite of this y coordinate, and that's what it means to be an odd function. So sine of x has the same property as that as well. So that's all we've got for this section. It's a pretty quick one. The things you need to know from here are that tanh is sinh over cosh, and you should know this identity, and you should know the derivatives of these here. Know the formulas for cosh and sinh, and know these. And that's all we have for the section. Hopefully I'll see you in class on Tuesday.